Now, ordinarily, when we apply an inverse function to get rid of a function, we want to end up with only numbers inside that inverse. But because power functions are relatively simple polynomial functions, we can solve radical equations that have occurrences of the variable outside the radical. We just might have to mess around a little bit. In this first example, we have an odd root, and so we don't need to worry at all about the range of our radical function. In other words, both our radical function and its inverse are 1-to-1. So when we rewrite in terms of the inverse, that's going to actually give us an equivalent equation. So, okay, we'd like to solve the third root of this polynomial, x squared plus 12x plus 19 equals x plus 1. And our first move, since our radical is already isolated, is going to be to rewrite that in terms of a power function. If the third root of this polynomial is x plus 1, this polynomial is x plus 1 to the third. And now I'm going to go over here and work out x plus 1 to the third. Right, that's going to be x plus 1 times another x plus 1 times another x plus 1. Multiplying the first two, that's going to give me x squared plus 2 times 1 times x plus 1 squared. And then I've got a third copy of x plus 1 along for the ride. So x squared plus 2x plus 1 times x plus 1. I'm multiplying something with 3 terms times something with 2 terms. For that, I'm going to draw a rectangle. I'll want to have 3 columns and 2 rows. And I'll put my x squared plus 2x plus 1 across the top. I'll put my x plus 1 down the side. Then x times x squared is x to the third. X times 2x is 2x squared. X times 1 is x. 1 times x squared is x squared. 1 times 2x is 2x. 1 times 1 is 1. Adding up down the diagonals, I get x to the third plus 3x squared plus 3x plus 1. So going back to my original equation, x squared plus 12x plus 19 equals x cubed plus 3x squared plus 3x plus 1. Okay, now I want to get 0 on one side of my equation. And I think I'm going to keep the terms on the right because that's the only place I have an x to the third. So I'll subtract x squared. X to the third minus x squared is going to be 2x squared. I'll subtract 12x. 3x minus 12x is going to be negative 9x. I'll subtract 19. 1 minus 19 is going to be negative 18. So I've got 0 equals x to the third plus 2x squared minus 19x minus 18. I have 1, 2, 3, 4 terms here. If I'm going to solve that by factoring, I'll be able to do it by factoring by grouping. So again, I'm going to want to draw a rectangle. This time 2 rows, 2 columns. I'm factoring this time, so I'm going from the result of multiplication to the expressions I'm multiplying. I'll put my terms x to the third plus 2x squared minus 9x minus 18, just one per box. In the first row, my greatest common factor is an x squared. And then x squared times x is x to the third. X squared times 2 is 2x squared. X times negative 9 is negative 9x. Negative 9 times 2 is negative 18. So my right-hand side factors as x plus 2 times x squared minus 9. X squared minus 9 is a difference of squares. So I'll have 0 equals x plus 2 times x minus 3 times x plus 3. If that whole product is 0, one of the factors has to be 0. So I have x is negative 2, x is positive 3, x is negative 3. To check, we want to see that each of these numbers works in the original equation. So for x is negative 2, we'll say third root of negative 2 squared plus 12 times negative 2 plus 19 equals the third root of negative 1, which is negative 1. Meanwhile, negative 2 plus 1 also equals negative 1. So x equals negative 2 really was a solution. For x equals 3, we have the third root of 3 squared plus 12 times 3 plus 19. Working out the stuff inside the root, we get the third root of 64, which equals 4. Meanwhile, 3 plus 1 equals 4, so x equals 3 really is a solution. Finally, for x equals negative 3, we'll have the third root of negative 3 squared plus 12 times negative 3 plus 19. And that works out to, plugging in everything inside the root, the third root of negative 8, which is negative 2. And meanwhile, negative 3 plus 1 is also negative 2. So all three of those numbers really were solutions to our original equation. We had a variable outside the radical. When we rewrote this in terms of a power function, we got a polynomial equation. We solved that polynomial equation, and that gave us the solutions to the original equation with a radical in it.